Hello everyone, welcome to Marri Laxman Reddy Institute of Technology and Management, that is Mlritm, Dundigal, Hyderabad. So this is Mr. S. Rajkumar, working as an assistant professor for the Department of Electrical and Electronics Engineering in Mlritm, Dundigal, Hyderabad. So today my topic is, in this lecture series, today my topic is locus diagram of parallel LC circuit by varying variable inductance. So that is varying the XL of a inductance of a LC circuit. So that we are going to see in this lecture series. For that one, I am considering parallel LC circuit as shown in figure. So this is the parallel LC circuit. So here we are taking one inductance and one capacitance. So for inductance, the internal resistance is RL. For capacitance, the internal resistance is RC. So for a alternating applied voltage of 50 Hz or fixed frequency applied alternating voltage of V, the total current drawn by the LC elements is I. So this is the total current. So this total current is divided into two currents, IL and IC. So whereas IL is the current flowing through the inductance in this branch, IC is the current flowing through the capacitance. So that is in this branch. So this is the LC, parallel LC circuit. For this one, we have to draw a locus diagram of a LC circuit. For that one, so I am taking, this LC circuit as shown in figure. So locus diagram for parallel LC circuit by varying XL. So this is the case where XL element is varies, that is inductance, reactance is varying with respect to capacitive reactance. So this is the case. As we know that the current in a LC circuit, the current flowing through the capacitive bank or capacitive capacitance. So the current flowing through a capacitor IC is constant and RC, SC are fixed one, because current flowing through the capacitor is constant. So this IC is constant. Because why? Because we are considering resistance, internal resistance of a capacitor RC and the capacitor itself. I am fixing the capacitor. Of a LC circuit. So with a internal resistance of RC. So with this RC and capacitance is fixed, the current flowing through the capacitor IC is constant one. So whereas XL is variable, so IL is varying. With varying the XL inductance, inductive reactance of a inductance varying, the IL current flowing through the inductance is varying, whereas current flowing through the capacitor is fixed one. So here this is a constant, IC is constant because of RC and C are the fixed. So this current leads the applied voltage vector V OV by an angle TC is equals tan inverse XC by RC. So this is the case. So here simply I can say that the current in a capacitive circuit, the current is leading with respect to the voltage. So if you are taking a phasor diagram, so V as a reference, the current is leading. The current flowing through the capacitance is leading, whereas current flowing through the inductance is lagging with respect to the applied voltage. So this is the basic thing you remember. So because of that one, IC is leading with respect to the applied voltage vector OV by an angle of tan inverse XC by RC. So whereas current flowing through the inductance IL, current flowing through the inductance, so with the inductance of vector IL. So this is the current flowing through the inductance is the vector IOL. In the diagram we will see that vector. So voltage vector and current vector of a LC circuit. So here when IL is equals along the current vector. So along the x-axis are OIL vector. So current is maximum. That maximum value is equals V by R when XL is equals to 0. So this is the case where we discussed in a RLC series circuit also when XL is equals to 0. XL is the variable element. I am considering when XL is equals to 0, what happened to the current flowing through the inductance. So when XL is equals to 0, the amplitude of a current, the maximum current is the V by RL. So this is the maximum current when XL is equals to 0. So this can be seen while drawing the locus diagram of a LC circuit. So when XL is equals to 0, the current is maximum. The maximum value of current is given by V by RL. So this maximum current is in phase with the applied voltage V. So when XL is equals to 0, the current flowing through the inductance or in a circuit is maximum. So that maximum current is in phase with the applied voltage. So this is the case where XL is equals to 0. So by keep on increasing the XL value from 0 to infinity, what happens? So what about the magnitude of a current? So when we are increasing XL value from 0 to infinity, the amplitude is decreases to 0. So previously amplitude is 0, it is decreases to 0 value. So the amplitude of a current, the current is equals to maximum V by RL when XL is equals to 0. So the current is decreases from maximum value to 0 when XL is increases. When XL is increases from 0 to infinity. So this is also we can see in while drawing the locus diagram. So these are the points you need to remember. So you need to remember. So these points, based on these points only, we are going to draw a locus diagram. So as usual, we know that the angle is given by tan inverse in reactive component by resistance. So this is the tan inverse XL by RL due to the inductance of a circuit. So this can be seen in a diagram. So based on those points, I am going to explain the locus diagram as shown in figure. So this is the locus diagram of a current vector I. This is the total current in a LC circuit. So in parallel with the L, inductance and capacitance of a circuit. So when inductive reactance XL is varied from 0 to infinity. So this is the locus diagram of a total current vector. Here the current I is the total current of a LC circuit. So here first we have to draw a reference axis. Voltage I am taking as a reference. So this is a reference vector OE. OV is a voltage vector, reference vector. As usual, we know that due to the capacitance, current is leading with respect to the voltage. So this is a capacity. The current IC is given by or leads the voltage vector OV by an angle TC. Similarly, we know that by the basic, so I am drawing IL current. So OIL is the current vector through the inductive circuit. So through the inductance. So this current IL is lagging with respect to the reference axis. So here I am taking voltage as a reference axis. So with respect to the voltage, the current is lagging in a inductance. So current is leading in a capacitance. So this I drawn. These are the two current vectors with reference to this voltage vector with reference to the voltage vector. So here the XL is the variable. Here XL is the variable. I am considering the XL value from 0. When XL is equals to 0, the current is maximum. That maximum current is given by V by RL. So this is the vector. It is in line, in phase with the voltage. In phase with the voltage. When XL is equals to 0, the amplitude of a maximum current is given by V by RL. So this current in phase with the voltage. So this is the in phase with the voltage. So now I am increasing the value of variable element XL. So I am increasing the variable element XL from 0 to infinity. I am increasing. So from 0, this is the 0 value of XL. I am increasing 0 to infinity. So this is the infinity. So 0 to infinity, the current magnitude, the current vector, the path traced or tip of a current vector traced by the path. So this is the current vector. So this is decreases. Maximum value to 0 value, the current is decreases. So here by increasing the XL value, from 0 to infinity, the current amplitude of a current, so that is current. So the current is decreases to 0. When XL is equals to infinity, the current is equals to 0. So this is the path traced by the tip of a current vector IL in inductance for the LC circuit. So here this is the locus. The path traced by the IL itself is the locus diagram for IL current vector of IL. So this is the locus diagram of IL. So to get a locus diagram for total current in LC circuit. So to get that locus diagram for total current of I. So total current of I, how to get a locus diagram. So for this one, so go to some points. Some points are there. Here some points are there. So here if we know that to get the sum of two vectors geometrically, we have to place one of the vectors starting point. That is here it is a variable element or a variable current, that is IL is varying. So that is the starting point of a IL at the tip of other vector. Other vector here is the current flowing through a capacitance, that is IC. So then joining the start of a fixed vector IC to the end of a variable vector IL. So based on this principle only, so I am going to draw a locus diagram for total current of I. So using this principle only, we can get the locus of a total current vector OI as shown in a figure. So here, so this is the diagram. So here you can see the locus of a total current I. So here the tip of a, so I am drawing a IL circuit here. So from this tip of a IC or a fixed current, so this is the tip of a current traced by the fixed current IC. So here from this joining point, from this joining point, I am drawing a semicircle like this, semicircle with a radius of V by RL. So with a radius of V by RL, I am drawing a circle or path traced by a tip of a IC and tip of a variable element IL. So this is the point. So the point of locus of this point C. Let us consider the point C. So this locus of a point C gives the locus of a total current I in LC circuit. So I hope all you understand. So this one, here the simple. So here the simple. So we are considering voltage as a reference. So this is the voltage vector. As usual, we know that has a phasor representation of a vectors or phasor diagrams. So our current is leading through the capacitor, current is lagging with respect to inductors. So in inductor, current is lagging, in a capacitor, current is leading. So here XL is the variable element, that's why I am changing from, I am considering 0 value, XL is equals to 0, the current is maximum V by RL, the maximum current in phase with the voltage, so I drawn here. So XL I am changing, a value of XL I am varying. So from 0 to infinity I am changing. So XL I am changing 0 to infinity. By changing the infinity, by changing the value of XL, variable element XL, the current is also changes, or current is decreases. Current is decreases from maximum value to 0 value. So current is 0 at XL is equals to infinity. So this is a current vector of in RLC circuit similar to the series RLC circuit. When XL is varying, resistance is constant. So this is the case of XL is varying, R is constant in series RLC circuit. Similarly, here in LC circuit, we are going to draw a locus of a total current vector I. So for that one, so I am taking a starting point of a IL circuit, and starting point of a vector IL, and the tip of a fixed current IC. I am considering a tip of a fixed current IC and starting point of a IL. So by combining these 2 points, here we are getting some point C. So this is the point which represents the locus of a total current. So I am drawing along with this one, I am changing the diameter with respect to the fixed current IC. So here we are getting a semicircle of with a diameter of V by IL. So this is all about locus diagram of a LC circuit with varying XL. So this topic I taken from a reference source of Google. So this is all about the locus diagram of a LC circuit with by varying the inductive reactance of XL. So thank you everyone. So I hope you understood very well. Thank you all.